So let's continue our discussion about the fork join pull framework. One of the things you've hopefully begun to realize by this point is that programming the fork join framework is more complicated in a lot of ways than trying to program the parallel streams framework. And that's because there's so many more moving parts in this framework that you have to sort of be aware of. You've got to know the interface for fork join pull, to know how to have non-fork join clients start the ball in motion. If you look at the assignment 3A skeleton, you'll see how I do that for you. I think I use invoke in one of the first methods or something like that. But the point is that you kind of have to know how to do that. You have to understand how to do fork and join. You have to understand how to subclass from recursive action or recursive task. There's just a lot of things to keep track of. In contrast, programming with the parallel streams framework, it provides you with a nice wrapper or a facade around all of the fork join pull machinery, and you just have to worry about providing these behaviors in the form of lambda expressions or method references that will run in parallel as you see, as the fork join pull under the hood sees fit. So it's a lot more convenient. So yet we still need to understand the fork join pull. So I'm going to start talking now about how it works internally. And hopefully, as you get a better sense of how it works internally, it'll make more sense how you program it. Because the problem is it's a little mysterious at first when you see how it's programmed. If you don't really understand the internals, it's like, how the heck is this even working? All this stuff is kind of being done implicitly. So we're going to talk about how the fork join framework implements worker threads in a worker pool, be it a common worker pool, the common worker pool, or a specific worker pool. So the way to think about this is, and let's just assume we have a fork join pool. It doesn't matter whether it's the one and only common one or not. It's got a bunch of threads in it, and each worker thread, which is actually a Java thread in the fork join pool, runs a loop that continually scans for tasks or subtasks to execute. So I always enjoyed this little animation because it's showing the worker threads just sitting there kind of spinning, doing something, waiting for work to do. And that's really the right metaphor to have in your mind. The reason why it's the right metaphor to have in your mind is that the goal is to try to keep the worker threads as busy as possible. So we want them to always have something to do. So how does this work? Well, you've got this pool of threads. Remember, the work gets into the pool of threads by some non-fork join task client saying, here, I'm going to submit a fork join task, or I'm going to invoke a fork join task, or I'm going to execute a fork join task. So somehow stuff gets into the pool of worker threads. And each worker thread has this double-ended queue, which is called a deck, that serves as its main source of tasks, above and beyond this other shared queue that's used to get non-fork join tasks into the fork join pool in the first place. So once things are in there, then these queues, these work queues or decks, are what's used henceforth. And the decks are implemented by something called work queue, which is a Java class that's nested inside of the fork join pool. And I won't go through this in detail, but I will just point out a couple of methods that are important. Push and pop are really important, and poll is also very important. There are other things here that do other stuff, but those are some of the key methods. So if a fork join task, which could be a recursive task, could be a recursive action, and so on, if the task that's running by the worker thread, however it got into the worker pool, calls fork, then that new task is pushed onto the head of that worker thread's deck. And I know I've said this a couple times, but it just bears repeating because it's so mysterious. So whenever you're calling fork inside of, say, a compute method in recursive task or recursive action, that's always running in the context of a thread in the fork join pool, because otherwise how could it run, right? So it's now inside the fork join pool. When fork is called, it turns around and pushes the task onto the work queue. And so as you can see here, it goes ahead and uses this push method to do that. So it pushes it onto the queue, and it pushes it in so-called LIFO order, last in, first out. So just like a stack, everybody knows a stack, hopefully at this point. Think about a stack of cafeteria trays at some place where you would go that was like a cafeteria, and so it's last in, first out. So you push it on there. And then when someone joins with a task, the task will be popped from the head of the deck, from the top of the stack, if you will, because remember, a deck has got a stack and a queue kind of munged together. It's a double-ended queue. The task is popped from the head of the deck and is run to completion in the worker thread. So we pop, we join, we pop, and then we process whatever is needed by that task, which is typically the compute method, as we just saw, right? Remember we saw how the compute method is what gets called back, and that actually does the work of the task. And this runs to completion. So what that means is it'll keep running until it's done. Now, if it happens to block, then other threads could run, but it's going to keep running until it's finished. And recall what we talked about before, that join pitches in to pop and execute these subtasks. So when you join, it'll keep executing other subtasks till we get back the results for our subtask that join was called on. And that's that cooperative Jiffy Lube model of processing we talked about before. Now, why do we do last in, first out? Why do we always push at the front and pop at the front? That's in order to improve locality of reference and therefore potentially get a better benefit from instruction and data caching. And these instruction and data caches are what are used by the cores in order to try to keep fresh work in the cache so that you get the processing as quickly as possible. Sometimes called fresh work before stale. Yes, Gavin? Oh, great question. So the question is, if we're doing this thing in LIFO order, last in, first out order, wouldn't it be possible for someone to get pushed, towards the end of the queue, other stuff gets in the front, and it gets ignored? The answer would be yes, if not for this other cool property we're about to talk about, which is work stealing. So work stealing is what prevents that from happening. It prevents things from getting lost. Okay, we'll talk about work stealing in just a second, but that's essentially how worker threads work. So worker threads take work, they do some computation, they fork, which pushes things onto the deck, and then either that worker thread will pop it when join occurs, or as we'll see in a second, the task will get stolen.